Okay, welcome students. In this video, we're actually going to start to learn chemistry. We're going to start chapter 1, which is titled The Structure of the Atom. And so have your guided notes out, ready to fill in any blank spots as we go through these slides. But let me give you an overview of what this video will cover. We're going to cover we're going to go back in time and look throughout history. We're going to look at those scientists that contributed to our knowledge currently of what the atom is, how it's organized, some of the different models that they use to explain it throughout history. We're going to look at how they were able to discover some of the parts of the atom, and then we're going to talk briefly about the different particles found in the atom. And so if you look at this slide here, I just went online and typed in atom in Google, and these were some of the images that came up. And so you see a typical atom has, a center and some particles in there, and a particle on the outside. Same thing with this model of the atom in the middle and on the right side. And by the end of this chapter, we're going to know a lot about how the atom is made up, what particles make up the atom. We're going to learn who it was, what scientists contributed to our current understanding of the atom. And so hopefully we'll learn a good deal about the basic unit of matter, which is the atom. So that's kind of our plan. So if you look at the development of the atomic theory, the atomic theory is just this theory that all matter is made up of atoms. Okay? And so even though atoms are too small to see, even with microscopes, we know a lot about them from experiments. And there's been a lot of really smart people and scientists that have contributed to our understanding of atoms, but they do it through experiments. Because even today, we can't see a detailed image of an atom, even with the best microscopes that we have today. Throughout history, many people have contributed to the atomic theory. It's been a lot of people have contributed to this, and it goes back to even as far back as 440 BC. So 440 BC to present day, we have continued to learn about the atom. And in this video, we're going to go through the history of that. And so if you look at 440 BC to present day, which is 2016, and if you do the math on that, that's 2,456 years. So we're talking about a lot of time that has gone by since people started to think about matter and what's the smallest unit of matter and think about atoms that way. So our knowledge of atoms has changed throughout history because of two things. Number one, scientists build on the knowledge of other scientists. So you have a scientist and he discovers a lot about the atom, and then he dies. Well, his work can be used by other scientists. They pick up his journal articles, they read it, they do some experiments to further his ideas and take our knowledge of the atom even farther. And that's continuing today. The second reason is because of technology. Technology is always improving, especially today. In 100 years from now, we're going to have some technology that allows us to learn even more about atoms. And so technology increases, so will our knowledge about the atom. Okay, so going back to the very beginning, who was the first person to start thinking about matter and about atoms? It was this guy here. His name was Democritus. Democritus was a Greek philosopher who started the atomic theory around 440 BC. So he's from Greece. He was a philosopher. What does that mean? Well, he philosophized. He was thinking, made thought experiments, and was thinking about matter and what makes up matter. And he started thinking about taking matter into its smallest, the smallest unit. So around 440 BC, a Greek philosopher named Democritus started imagining the smallest piece of matter. He imagined cutting something in half, and then cutting it in half again, and again, until maybe it couldn't be cut in half again. In class, I always use the analogy of a mechanical pencil lead. Well, it's not really lead, but graphite. So if we take this line right here, imagine that's a piece of lead or a piece of graphite from your mechanical pencil, and if we cut it in half, okay, now it's only half as long, and do that again. Well, this piece of graphite, if you keep cutting it in half again and again and again and again, you're going to eventually get down to a piece, according to Democritus, that you wouldn't be able to cut in half again. So imagine doing that, cutting it in half again and again and again, and you're going to get to a piece that you couldn't cut in half. Well, Democritus called this piece of matter that was so small that it could not be cut in half again, he called that an atom. And so that's where the term atom comes from. The word atom is from the Greek word atomos, meaning not able to be divided. So that's what atom means. Literally, in the Greek language, not able to be divided. And so ever since Democritus, which was 440 BC, we've had this word atom, meaning not able to be divided. And that's, we still use the word atom today to mean the smallest or the basic unit of matter. And so Democritus thought that atoms were made of a single material formed into different shapes and sizes. Now think about it. 440 BC, not much technology back there. If you were just doing thought experiments on matter, yeah, that's pretty plausible. Matter is made of a single material, but just has different shapes and sizes. Now, of course, not all of Democritus' ideas are still 100% accurate today. We've changed it throughout history. But he was the first person to start thinking about matter and what makes up matter. So, okay, from Democritus we go to Aristotle. Aristotle was another Greek philosopher who disagreed with Democritus' ideas. So he disagreed with Democritus. Aristotle believed that you would never end up with a particle that could not be cut in half. So if you think about it in terms of, like in mathematics, you could always cut a number in half. Well, you take 4. Well, it goes to 2, then 1, then 0.5, and always, you're always going to be able to cut a number, or in this case, matter, in half. And so that's how he disagreed with Democritus. So, in terms of matter, who was right? Democritus or Aristotle? It turns out that in terms of matter, Democritus was right. Matter is made up of particles, which we call atoms. And this is a great definition for what an atom is. An atom is the smallest particle into which an element can be divided and still be the same substance. This is kind of key to that definition. And still be the same substance. We have learned a lot about atoms since Democritus' time. In fact, we've learned how to split atoms. We can cut them in half and split them. But when you do that, you split an atom, it becomes some other element. It makes some other substance. And so this definition for atom is one that I really like, and it kind of reinforces what Democritus was trying to say clear back at 440 BC. So, from 440 BC until about the 1700s, so from 440 BC to the 1700s, that's over 2,000 years. The Earth, in that period of time, went through what is known as the Dark Ages. And the Dark Ages wasn't called the Dark Ages because it was literally dark. It was called the Dark Ages because nobody really valued education. Nobody really took people's knowledge and wanted to build on it and further our knowledge in certain subjects or any subjects. And so they're known as the Dark Ages. But when we hit the 1700s, we call that period of time the Enlightenment or the Renaissance. And people started to revalue education, and we wanted to build upon knowledge, and we wanted to learn about why things are the way they are. and figure more stuff out. Well, John Dalton was that person for chemistry. John Dalton was a British chemist and school teacher who lived in the 1700s. His experiments showed that elements combine in certain proportions. For example, hydrogen. If you mix it with oxygen, it will always combine when you form water into a certain proportion. Water is always 2 hydrogens and 1 oxygen. So if you form water, it's always going to be 2 hydrogens and 1 oxygen. And so he showed that elements combined in certain proportions, just like that. And he did a lot of experiments, and he really helped to bring about this renewed interest in chemistry and bring that back into the forefront. Okay, Dalton's theory. We can summarize Dalton's work in 3 principles. Number 1, all substances are made of atoms. John Dalton said that everything, all substances, are made of atoms. Atoms are a small particle that cannot be created, divided, or destroyed. Now, of course, we know that we can divide them, we can split the atom, but in John Dalton's time, the early 1800s, this is what was known of the atom at that time. John Dalton also said that atoms of the same element are exactly alike. So if you find an oxygen atom in the United States, and you find one in a different part of the world, China, they are going to be just like each other. No matter where you find oxygen in the universe, it's always going to look like oxygen. And atoms of different elements are different. Okay, so oxygen is different than hydrogen. They're just different. Okay, his third thing. John Dalton said that atoms join with other atoms to make new substances. So we can combine hydrogen and oxygen, and we can make a new substance, water. Both of these are a gas. Hydrogen's a gas, oxygen's a gas, but when they combine, it makes liquid water. And so you can combine atoms to make new substances. So John Dalton, very important in the history of the atomic theory. Okay, John Dalton in 1807 proposed a billiard ball model of the atom. And we're going to go over the models of the atom and how they have changed throughout history. But a model is just a visual representation of what we believe at that time to be correct of the atom. And so for John Dalton, he said that atoms were small, were very tiny, indivisibly, uniformly dense, solid spheres, just like a billiard ball would be. So just a very hard, small particle. And so we call it the billiard ball model. Dalton's theories weren't quite correct, though. By the late 1800s, scientists began to get a new information about atoms that didn't quite fit Dalton's theory. So it was changed step by step into today's modern atomic theory. And in the coming slides, we're going to go step by step on how this theory, the atomic theory, has changed into what we believe to be correct today. And one of the guys to do that, to change Dalton's theories, was this guy. His name was J.J. Thomson. So in 1897, so in the late 1800s, a British scientist named J.J. Thomson showed that there were small particles inside an atom called electrons. So he discovered this particle called electrons. J.J. Thomson experimented with cathode ray tubes. So he did a cathode ray tube experiment that we're going to describe in great detail in the coming slides. But he used the cathode ray tube to show the existence of electrons. And it's very clever. We'll show you how he did that in the coming slides. He won the Nobel Prize, which is the highest, the most prestigious prize in science, in 1906 for the discovery of the electrons. So, cathode ray tube experiment. Let's go through what a cathode ray tube is. It's a glass tube, as shown here. It's a glass tube, but they take all of the air out of it. So there's no atoms in there. There's no oxygen. There's no carbon dioxide or hydrogen or nitrogen in the tube at all. It's all empty. So there's no atoms in there. And what he did was he passed electricity through it. Okay? And the electricity passed through it, and it would pass through, and you could see it. But the clever thing that he did was that he put on each side of the cathode ray tube, he put a magnet and magnetic field. On one side was positive, and on the other side was negative. And so he passed this electricity through it, and on the positive side, he noticed that this beam of particles would be deflected toward the positive side. Okay, and it would be deflected away from the negative side. So he knew that there was a particle, and this particle was influenced by a magnetic field. Now, if we go to magnetic charges here, if we have two positive charges, and we were to let go of them, say we brought them together and we let go, well, two positive charges would repel each other. Like charges repel, but what if you brought in a positive and a negative particle? They are going to attract each other. So opposites attract. That's where that saying comes from. Positive charges are attracted to negative charges. Well, what if you had two negatives? Again, they would repel each other. And so opposites attract, like charges repel. And so knowing that, he knew that this particle, there must be a particle in this beam that was attracted to a positive magnetic field. So he knew that these particles had to have a negative charge. And so Thomson concluded that the beam was made of particles that have negatively electric charges. These negative electric charges are particles that Thomson discovered and are now called electrons. So I've got some slides coming up that will, and even some videos that will explain cathode ray tubes and show them to you. Okay, so here's a clip I pulled off of YouTube. Hopefully it works and you can hear the sound. If not, you can go to the slides later and listen to it just through YouTube. But I'm going to hit play and see if this works.
Okay, this is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are two electrodes. One's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thomson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray, and he found something interesting. We apply one pole of the magnet to this beam, and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam? What does it appear as though it's happening to it?
It's moving.
It's moving. It's being repelled, isn't it, by the magnet? When we flip the magnet around, what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively charged particles. And J.J. Thomson was actually able to do a charge to mass ratio of these particles, and he found that these particles were about 2,000 times lighter than a hydrogen atom. Now at the time that was very profound. What did Dalton say? Are there any particles smaller than an atom? J.J. Thomson just found something 2,000 times smaller than a hydrogen atom. Why is the hydrogen atom and something 2,000 times smaller than it so profound? Because hydrogen is the smallest atom, isn't it? So if we found something 2,000 times smaller, we have found our first subatomic particle. And it's called the electron.
Okay, so that video is a great video. I wish I had one of those cathode ray tubes, but they're pretty hard to find nowadays. And so it shows you, and he was showing with a magnet how that beam of electrons was influenced in a magnetic field. And so that's how J.J. Thomson was able to discover electrons, even though we can't see electrons. We even today cannot see electrons. And it's just a very clever experiment, and one that's very famous in science. And so we've got to know that the electron was discovered by J.J. Thomson, and he did so by conducting the cathode ray tube experiment. Okay, so the electron. Matter is neutral. You know that matter is neutral from everyday experience. You do not receive an electric shock when you touch something, except under certain conditions. So when I touch the counter, it doesn't shock me. So if there's negatively charged particles, like the electron, and J.J. Thomson found that it was negatively charged, there must be other particles inside the atom, okay, that must be positive, because it's got to balance out that negative charge. So if electrons are negative, then how is matter, which is made up of electrons, neutral? Well, there must be positive charges in the atom somewhere. And so J.J. Thomson proposed a model of the atom to answer this question. So remember the model of the atom that we had up to this point, John Dalton's billiard ball model. Now J.J. Thomson discovers the electron, so we've got to add to that model. We've got to modify it a little bit. And J.J. Thomson did that, and he called it the plum pudding model. It was a popular dessert at his time, plum pudding. And so his model of the atom looked like this. The plums in this plum pudding were the electrons. I think of it as a chocolate chip cookie, and the chocolate chips were the electrons. Now we know that the atom can't be negatively charged because matter doesn't shock us when we touch it. There's got to be some positive charges in there somewhere. And he said that the positively charges were evenly distributed throughout the pudding. Or if you're thinking about it like a chocolate chip cookie, it would be the cookie dough. Okay? So all of this stuff here was positively charged. And then there's particles, or plums, or chocolate chips that were negative. And so that's what the model of the atom looked like during that time after J.J. Thomson discovered the electrons. It's called the plum pudding model. Okay, so scientists build on other scientists' knowledge of the atom. Another guy to come along and change it a little bit was this guy, Ernest Rutherford. He lived from 1871 to 1937, so into the 1900s here. In 1909, Ernest Rutherford discovered the nucleus of the atom. So he discovered the nucleus of the atom. Rutherford used a very clever experiment again. This experiment was called the gold foil experiment to show that atoms have a small but positively charged nucleus. Okay, so atoms have a small, positively charged nucleus. And Ernest Rutherford proved that using the gold foil experiment. In the coming slides, we're going to show you what the gold foil experiment and how he was able to show the existence of a nucleus and that it was positively charged. A very clever experiment, and it's a little more complicated, so I'm going to spend some time talking about it. Okay. Also, Ernest Rutherford was the first person to split an atom. Element 104, if you look at it on the periodic table, it's called Rutherfordium, was named in his honor in 1997. The people that discovered that named it after him. So, okay. Ernest Rutherford discovers the nucleus of the atom. In 1909, a former student of J.J. Thomson named Ernest Rutherford. So that's interesting. Rutherford was a student of J.J. Thomson. And he tested the parts of the atom, and he won the Nobel Prize in 1908. Again, the highest, most prestigious prize in science. He aimed a beam of small, positively charged particles at a thin sheet of gold foil. Gold foil is just like aluminum foil that we have today, but it's made of gold, obviously. But he aimed a small beam of positively charged particles. These positively charged particles that he shot at this gold foil are called alpha particles. Okay? And so that's a key to his experiment. I want you to remember that the particles he was shooting at the gold foil were positively charged, and he knew that at the time. So Rutherford put a special coating behind the foil, and this coating glowed when it was hit by a positively charged particle, so he would know where the particles were going. Here's kind of a diagram that shows a gold foil experiment. This is the alpha particle emitter over here. Remember, these alpha particles are positive, and he knew that. Okay, so he put it in a block of lead and a small hole allowed it just to go in one direction. This is the gold foil, just like the aluminum foil, but it's made of gold. And then he put this detection screen around it that would light up when an alpha particle would hit it. And what he noticed was that when he started the experiment, these alpha particles would come, and most of them would cause that screen to light up straight through. Okay? But what he didn't expect to find was that sometimes these alpha particles were deflected. Sometimes at small angles, like this one here, but sometimes at larger angles. And even some of them would come almost straight back. So that was an unexpected finding. And so he tried to explain what was happening. What was causing this positively charged particle to be deflected? Remember, if you have a positive particle, what would deflect a positive particle? Well, another positive particle. They don't like to be by each other. They will repel each other. So he hypothesized that there must be something in the atom that's positively charged. And he called that region of the atom the nucleus. And protons, which are positively charged, those are the positively charged particles that make up part of the nucleus. So most of the particles went straight through the gold foil as expected, but some particles were deflected. This was an unexpected finding. So he discovered the nucleus this way. The repulsive forces between the positively charged nucleus and the positive alpha particles cause the deflections. And so when he shot an alpha particle, which is positive, at that gold foil, that alpha particle would sometimes be hit or hit the nucleus of an atom. And if it did, it would cause it to deflect. Because positive and positive don't like each other, they repel. But what he noticed was that most of the particles would go straight through. So they didn't hit the nucleus at all. So that showed him something else. That told him that in terms of size, the nucleus was very small compared to the whole size of the atom. The nucleus is very small. Because most of them went straight through, weren't deflected at all. So the nucleus he found was very small, and it had to be positively charged. This is another clip I pulled from YouTube. I hope that you can hear it, so we'll give it a shot. It just explains the gold foil experiment again.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, I wanted to pause it at that point.
At a large angle.
Oh, good. I wanted to pause it right here and show you and just emphasize the point of the gold foil experiment. These are the alpha particles. Most of them go straight through because they don't hit a nucleus. But every once in a while, that alpha particle, that positively charged particle, would come in contact with this part,
Encounters
with this part of the atom, which is the nucleus, and it would bounce off because the nucleus is positively charged. So it showed Ernest Rutherford that in terms of size, the nucleus is very small. The atom, where the electrons are, is very large. And so that was a key finding. Okay. Okay, I've got another video from YouTube, and this one shows the gold foil experiment, but it's put on in a real lab, and it's kind of a modernized gold foil experiment, and it does a great job of explaining what the gold foil did and how it was able to show that there is this existence of a nucleus. And so let's watch this. It's kind of long, but I think it's worth it.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter, we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom is empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, what we're doing here, is taking a beam of particles, firing them at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behaviour of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometres in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom by comparison is very big, so it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
Okay, so hopefully that gives you a better idea about what the gold foil experiment did and how Ernest Rutherford was able to discover the nucleus and know that there was a positively charged nucleus to the atom. So Rutherford's conclusions. He concluded that the atom must be considered mostly empty space with a tiny part made up of highly dense matter. In 1911, Rutherford made a new model of the atom. So we've gone from John Dalton's billiard ball model to J.J. Thomson's plum pudding model to now we have a new model of the atom because now there's a nucleus. And he also discovered and named the proton. Rutherford's model, the center of the atom was very tiny, dense, and positively charged. He called the center of the atom the nucleus. Rutherford found that the nucleus is 100,000 times smaller than the diameter of the atom. So if the electrons are out here, 100,000 times smaller than the diameter of the atom, I couldn't even draw it small enough, the nucleus would be very, very small. So what's happening in all this space here? It's just empty space. It's where the electrons are hanging out. And so now we have a new model of the atom. And here's a picture of Rutherford's model. So again, we have this nucleus. It's positively charged. It's got protons in there. And we have around the outside these other particles that J.J. Thomson discovered, the electrons, which are negatively charged. Okay? And so that's how the model of the atom changed through Rutherford's time. Okay, the nucleus. Rutherford concluded that the atom are mostly empty space. Here's a good definition for a nucleus. So a nucleus is the tiny, dense region in the center of the atom. Most of the atom's mass is found here, and it's positively charged. Now that's an important point. Most of the mass of the atom is found in its nucleus. But the nucleus is very small compared to the size of the atom. And so those are some of the important points that Ernest Rutherford was able to find. Electrons are also held within the atom by the attraction to the positively charged nucleus. That's an important point. Electrons are held within the atom by their attraction to the positively charged nucleus. Let me explain that. Let's go back here to this slide. If the nucleus is positively charged, these electrons are held here. Remember that opposite charges attract each other. And so these electrons are being held closer to the nucleus because of those opposite charges. Remember, opposites attract and charges and like charges repel each other. Okay, let's move on from Ernest Rutherford and let's go to another scientist who contributed to our understanding of the atom, and his name is Niels Bohr. Niels Bohr is in this picture, and he's sitting next to somebody you might recognize, somebody very famous. So this is Niels Bohr right here. But who is this guy? That's Albert Einstein. You probably recognize him. And they were good friends and did a lot of work together. Niels Bohr, though, let's focus on him for a second, was a Danish scientist who contributed to our knowledge of the atom. He won the Nobel Prize in 1922 for his work. In 1913, Niels Bohr proposed that electrons move around the nucleus in certain paths called energy levels. So what I want you to remember about Niels Bohr was he said that electrons move around the nucleus in certain paths called energy levels. So when I say energy levels, you should think Niels Bohr. Okay? Here's a model of the atom that Niels Bohr came up with. Okay, Niels Bohr proposed that electrons travel around the nucleus in specific paths called energy levels. So here's our nucleus that Ernest Rutherford discovered. It's positively charged. But Niels Bohr said that the electrons were out here, and they would kind of go around the nucleus in circular paths called energy levels. And so this is energy level 1. 2 would be just a little bit further out. 3 is a little bit farther out. And 4, and it continues to go farther out. And so in circular paths, these are called energy levels. So E1, E2, E3, E4. This is Niels Bohr's model of the atom. Okay, and it changed one more time before we get to our current. These guys changed it into our modern atomic theory. These guys here, Werner Heisenberg and Erwin Schrödinger, came up with the electron cloud model. So this is the according to this model, this electron cloud model is what we consider to be the most correct today. And so this was the last change that was made to the atomic theory. So according to the current theory, there are regions inside the atom where electrons are likely to be found, but we have no idea about their path, their speed, or their direction that they're traveling. But these regions are called the electron cloud. So we no longer consider Niels Bohr's model of the atom with energy levels to be correct. We just call it an electron cloud. Heisenberg and Schrödinger proved that we can't know exactly where the electron is going. It's not going in circular paths, but we just call it an electron cloud. And so we kind of represent it with this vague kind of outline, kind of like a cloud, a real cloud. And so somewhere inside this cloud, there's the electrons are found, but we don't know exactly where they're at or what direction they're going at any moment in time. And so that's the theory that we consider to be the most correct today. It's called the electron cloud model of the atom. Electron cloud. Okay, so here's a slide that kind of summarizes everything that we've talked about so far in the development of the atomic model over time. So this is a good timeline. Dalton's model. Remember, John Dalton, billiard ball. He said that atoms are just small, hard particles. And for that time, it was a pretty good model. Then we had the Plum pudding model. J.J. Thomson discovered the electron through the cathode ray tube experiment. So this plum pudding, these are the electrons, the plums. Or I think of it as a chocolate chip cookie. These are the chocolate chips. Everything around the chocolate chips, I'm sorry, that's the negative. Everything around these chocolate chips was the positive region. So this pudding inside, or the cookie dough, if you think about it as a cookie. So that changed a little bit because we discovered the electron. Okay, well, Ernest Rutherford discovered the proton in the nucleus. And so we now know that there's this center of the atom called the nucleus, and that the electrons must be around the outside doing something. Okay? Well, then Niels Bohr came up with the energy level model. He said that electrons travel around the nucleus in circular paths called energy levels. Okay? Well, Schrödinger and Heisenberg showed that that's not quite correct. They came up with this quantum model, what I really call it the electron cloud. The electron cloud model. And so we know that the electrons are not traveling in circular paths, but they're somewhere out here on the outskirts, but we don't know its definite shape. Okay? So from Dalton to J.J. Thomson to Ernest Rutherford to Niels Bohr and to the electron cloud model. Hopefully that's a good summary of how we've learned about the model of the atom through time. So an atomic theory timeline. I would like you to make a poster or just on a piece of paper that shows the major discoveries about the atom throughout history and include what each person contributed to that theory. Let's go through it. So it started off with Democritus. Atom. The word atom means not able to be divided. He just said there's a basic unit of matter and it's called the atom. It can't be split anymore. Not quite correct. Aristotle said you could continue to split it forever. We know that Aristotle's ideas were not correct. Dark Ages happened. 1700s, the Enlightenment, the Renaissance began. John Dalton came up with the billiard ball model. Okay, he said that atoms are small, hard, dense particles. J.J. Thomson discovered the electron. So then we come up with the plum pudding model. We have some electrons in here, like a chocolate chip cookie. 1911, Ernest Rutherford came, and he threw the... well, first of all, let's go back to J.J. Thomson. How did he discover the electrons? It's with the cathode ray tube. You got to know that. He discovered the electrons by using the cathode ray tube. Okay, that was his experiment that showed that they exist. In 1911, Ernest Rutherford changed the model of the atom. Well, Rutherford used the gold foil experiment to show the existence of a positively charged nucleus. So now we have a positively charged nucleus. It's very small. We've got electrons around the outside. We don't really know what they're doing, but we know that there's a positively charged nucleus and it's very small. Okay? Named the proton. Then in 1913, Niels Bohr changed the model of the atom. He said that around the nucleus, the electrons are traveling in circular paths called energy levels. Well, then in 1933, Erwin Schrödinger and Werner Heisenberg changed it again into what the model of the atom that we consider correct today is the electron cloud model. So yeah, we still have a nucleus, but there's this cloud out here. We don't really know what the electrons are doing, but they're certainly not going in orbits or circular paths called energy levels. Okay, so hopefully that helps you. I think we'll stop the video there. Helps you understand how we are able to understand what the atom is, what particles make it up, how people were able to discover the electron, the nucleus, the proton, and make a little bit more sense of how all of this came to light. Hopefully that helps.